This is going to be a video on capacitor charging up. I did the discharging one before. This is kind of the opposite, but there's a little bit of nuance here, and I will kind of say at the beginning that IB doesn't really need you to know this. So many of you just turned the video off. They really want you to know the discharging, which I just did here. The charging up is kind of interesting, but they just tend to not deal with the charging up. They kind of go with the discharging and leave it at that. But it is in the curriculum, so there's a chance. Here it is. If I change this, if I close this switch, there's now a cell in here, and it's gonna shove charge onto my capacitor. So you're gonna have electrons moving this way. And this is gonna start to fill up quickly at first because there's no repulsion when you start. And then as it starts to fill up, now it's harder and harder to push more electrons in there. And of course, when you pull electrons around the circuit, you're gonna be left with positive charge on the other side. If you graph this, it looks as you might expect, and this is T. Kind of opposite, you start at no charge, and it quickly ramps up, and then as you get more and more electrons in there, it's harder and harder to deposit the charge. You can parse this out into time constants, just like we did with the discharge. This being RC. But this time, instead of going to 37% of charge, you have 37% left until your EMF. And so this is, in this case, V naught up here is equal to the peak voltage. It's the same thing. It's the EMF of the battery. It never quite gets to the EMF of the battery, but there you go. So let's say that this cell was 10 volts. Okay. So you would come up here after one time constant, you would be 63% of your EMF. Happens pretty fast. Why 63, you might ask? So this is 63% of the peak voltage, 63% of the EMF of the battery. So after one time constant, you would be 6.3 volts in this circuit, okay? And let's just say that our capacitance here is the same as it was before. Let's say 3 microfarads, and my resistor is still 5 ohms. That's from the last example. It doesn't really matter. After another time constant, you're going to be at about 0.63 squared V naught EMF, and of course here you're 0.63 cubed times V naught. And that carries on, keeps going. Okay, this is a 0. How can we write that? Well, it's kind of the opposite. We say here that V equals V naught, and this you could write as EMF as well. 1 minus e to the power of negative t over RC. And RC is still the time constant, tau, like we had before, so my time constant is RC. That's a simple little doodad there. So let's try a little problem here. Let's say that we're going to charge up this capacitor. It starts at nothing. It starts neutral, and we're going to charge it up to 2 volts. So you're starting from 0 volts, charging up to 2 volts, using a 10 volt battery. How long does that take? Okay, notice there's 3 voltage numbers here. The capacitor is going from 0 to 2, okay, but in this formula, this is the EMF. So let me write it again and just be really clear here, because this causes all kinds of gnashing of teeth, consternation. This is the EMF of the cell that's charging the capacitor. This is the power source, the battery. It's not necessarily the charge that the capacitor will reach. Okay, so if I'm going from 0 here up to here, let's say, this is not the full EMF, nor did I start at the full EMF, but I need to know the EMF because I'm on this curve that is approaching the EMF. So I'm gonna close this switch. I've got 10 volts, it shoots in there. At some point, we're gonna hit 2 volts. If I let it keep going, we're gonna get up and approach 10, but I wanna know when the capacitor is at 2 volts. This formula tells me that V is 2, but the E, it's not the initial voltage, it's not 0, it's the EMF of the battery, and it's the voltage that the capacitor will approach if left for a long time. Okay, so that's important here. Okay, so right now, pause this. I think you have all the variables you need, and try to solve for the time that it would take to charge this capacitor up to 2 volts using a 10 volt cell. Okay, hopefully you did that. I'm just gonna solve this. So we go V over the EMF of the battery. That's gonna equal 1 minus e to the negative t over my time constant. I don't like this negative here, so I'm gonna add this to the other side. And I'm gonna say that e to the negative t over c equals 1, and I'm gonna subtract over my voltage over EMF, and you could write this as V over V naught. You just have to know what it means. And then I'm going to continue this here. Hopefully you can see that. I want to get rid of this E, so I'm going to ln this. If I take the natural logarithm of e to the x, it's just x, which is quite nice. And that's going to be ln of 1 minus V over E. So this goes away, and I end up with negative t over RC is equal to the ln of all this. This is going to be just a number, but you'll notice if you do this wrong, if you get doing your IB exam or something and you think, well, this is my V and this is V naught, so I'm going to make this like 2 over 0 or something like that. Well, that's going to give you an error, right? If you say, well, let's do let's see how long it takes to go from 2 up to 10. Well, that's going to be like 10 over 2, which is 5, which is going to give you a negative number, and a ln of negative number, you're going to get an error. That's no good. So this has to be the voltage from 0 that you reach. So we're going from 0 volts up to 2 volts using an EMF of 10. Okay, the capacitor never hits 10 volts. But this is going to be okay because this is going to be the ln of 1 minus 2. That's the voltage we're going to reach over 10, which is my maximum voltage that I would reach if I let it go. Okay. I just wanted to put those numbers in to show you this is going to be 1 minus that, so it's a positive number, so my natural logarithm's no problems, okay? And of course, I want to solve for t, so I'm going to bring this negative RC over here, and I'm going to just make this, that would be 8 over 10, so 0.8. Because it's 10 over 10, and 10 minus 2 is 8, and so 8 over 10, and that's 0.8. Okay, so if we put those values in, we're going to have negative Neva, I smell gas. Did you start the oven? Neva, I smell gas.
Oven's on.
Just the oven? But it's lit? Okay, that's fine. As long as you don't have a burner going. R is 5 times the capacitance, which we said was 3 times 10 to the negative 6. And then I take times that by the ln of 0.8. And I'm going to get a time of 3.3 times 10 to the negative 6 seconds, or 3.3 microseconds. Now that is the time it takes for my capacitor to go from V equals 0 to V equals 2, okay? And you'll notice that if you were to do this again and make this 6 out of 10, then this would go to 0.4, and your time would be greater. And that's because if you take the time from 0 to 2, that's a certain amount of time, and if you go from 0 to 6, that's greater. If you wanted to know how to go from, like, what would be the time to go from 2 up to the full voltage of 10, or maybe we might say 9.9, otherwise it'd be a really long time, you could subtract the full time. Right, so we could do, if we put 10 out of 10 here, well, no, because then we get the one of 0, which is error domain. So, but we could do 9.9. If we wanted to say how long it would take to go from 0 to 9.9, this would be 9.9, and we would do 5 times, what was my capacitor? 3 times 10 to the negative 6 equals, and you're gonna multiply that by the ln of, if this were 9.9, you would do 1 minus 9.9 over 10, and you would get the time it takes for the capacitor to go from V equals 0 to V equals 9.9 is 6.9 times 10 to the negative 5 seconds, okay? And so this is, that would have to go down and stuff go up. So it's 69 times 10 to the negative 6. So 69 microseconds. And you would subtract this amount of time. So if you wanted to know how long it would take to go from 2 volts to 9.9 volts, that's this amount of time. You would take this. You can only use this relationship to go from 0 to some number, and you use the EMF as the V naught here in your equation. Okay, and so that would be 65.7 microseconds to go from 2 volts up to 9.9. I don't think IB is ever going to ask you that, but hopefully now you understand the discharging from the previous video and the charging up from this video.